Welcome to our deep dive on Meta's new Byte Latent Transformer architecture, BLT, as everyone's calling it. We've been getting tons of questions about it.
Yeah.
Is this a real breakthrough or just more AI hype?
Right.
And honestly, even as AI researchers, we've all been hitting the walls with tokenization.
Yeah.
Some of us are even a bit skeptical about this whole thing.
I can see that.
Like on Reddit, there's this user, 13house, I know, great username, right?
Oh, yeah, I saw that thread.
They were saying BLT won't fix those core transformer problems. Like, how they just can't reliably count things.
Right.
But still, the idea of finally ditching tokens.
Yeah.
And maybe even beating those traditional models, even with like 8 billion parameters.
8 billion.
It's huge.
Pretty intriguing.
Very intriguing.
So let's unpack this whole BLT thing.
Great.
Maybe we should start with, what problem is it actually trying to solve?
Yeah, that's a good starting point. So tokenization, which is like essential for transformers, always been kind of a bottleneck,
It's always felt a bit clunky to me.
Yeah, exactly. It's like you're trying to shove a square peg into a round hole.
Yeah.
You're representing this like complex information with these fixed units, and it doesn't always fit neatly.
And it never really felt like a perfect solution.
Yeah. Remember that quote from Andrej Karpathy?
Oh, yeah.
He said, tokenization is at the heart of much weirdness in LLMs.
That's a good one.
And he's absolutely right. Think about all those weird quirks.
Okay.
Spelling errors, problems with like simple string processing.
Yeah.
Bad performance with non-English languages, struggling with basic arithmetic.
Yeah, it can get pretty frustrating.
Yeah. All of those can be traced back to how we tokenize text.
It really is the foundation, isn't it?
It is. Like you're building a house on a shaky foundation. Even with things like BPE, which was better, for sure.
Right.
It was a step in the right direction, but we're still stuck with these pre-computed tokens. They don't always work perfectly.
Exactly. They're not always optimal.
Not perfect.
No. And that's where BLT changes things up.
Okay, so how is it different?
Instead of these predefined tokens, it uses these dynamic, learnable patches.
Patches?
Yeah, patches. And they're based on byte-level entropy.
So that's a big difference then.
A key distinction.
Okay, so let's talk about this byte-level entropy thing. What is that?
All right. So
I was looking at figure 4 from a Hacker News comment. It had this visualization of how byte entropy works in a sentence.
Yeah, I saw that. It was helpful.
It's really interesting how BLT determines patch size. Like, it's based on the uncertainty of the upcoming bytes, right?
Yes, exactly.
So each chunk has roughly the same information.
It balances it out.
Yeah.
So yeah, that figure 4, that was great.
It was.
It shows how BLT analyzes the uncertainty or entropy of each upcoming byte.
Right.
Imagine, the model's scanning the text.
Okay.
And it's checking the probability of the next byte. It's almost like the model's asking itself, how sure am I this next byte is an A or a B or whatever?
Right.
And then it groups these bytes into these patches.
Making sure each one has a similar amount of information.
Exactly.
That's pretty clever.
It is a very clever approach.
It kind of reminds me of how people speed read.
Oh, yeah.
Like, you focus on the word shapes and the key information.
And get the gist quickly.
Yeah. Like, BLT is speed reading, but for code.
That's a great analogy. It's essentially doing something similar.
Wow.
It adjusts the patch size dynamically based on the information density.
So it's not just about the total entropy then.
Right. Some people get that wrong. There was this user on Hacker News, Yoruba one.
Okay.
They pointed out correctly that it's actually about comparing individual byte entropies
Yeah.
against global and preceding byte thresholds.
Right.
That's all detailed in section 2.3 of the paper.
So it's constantly evaluating how much information each byte is carrying.
Exactly.
And grouping them accordingly.
Yes.
Okay, so how does that fit into BLT's architecture?
Well, BLT uses an encoder-decoder structure.
Like the classic transformers.
Just like traditional transformers. But here's the difference.
Okay.
In BLT, this encoder-decoder setup, it acts as a learnable tokenization scheme.
Learnable tokenization scheme.
Yeah. So it adapts to the data it's processing instead of being stuck with those fixed pre-computed tokens.
So it's basically learning how to tokenize on the fly.
Exactly. It's dynamic tokenization.
And that makes it more efficient.
Yes, it offers significant efficiency advantages because for those predictable byte sequences, the low entropy patches, the encoder can offload a lot of the work.
So the main transformer doesn't have to do it all.
Exactly.
Yeah.
Doesn't have to handle all the heavy lifting.
That's fascinating. It's amazing how often, like these end-to-end learned systems, they just outperform the ones we humans carefully design.
Right.
It's really interesting.
It is. Makes you think.
Do you think that's true for BLT too?
It's a good question. It's early days, of course.
Yeah.
But the benchmark results are looking good. The paper shows BLT outperforming BPE in terms of both performance and efficiency.
Even with those huge models.
Yep, even up to 8 billion parameters.
Wow. And it's not just about text processing.
No, not at all.
I've seen a lot of excitement about BLT for multimodal learning.
Oh, absolutely.
Like being able to process images and videos and sound.
Directly as bytes.
Directly as bytes.
Yeah, it's a very exciting possibility.
People are even talking about it being able to generate and edit binary files.
I've seen those discussions too.
Like give BLT notepad.exe and tell it to add a new feature.
Yeah, wild.
It sounds like sci-fi, but with BLT working at the byte level, it actually seems possible.
It's becoming more tangible.
It's crazy. The applications are mind-blowing. Like game remastering.
Oh, yeah. I saw that comment.
Imagine taking an old game's binary.
Right.
And having BLT update it with modern code.
Keep the gameplay, but with new features.
Exactly. I saw someone mentioning stars.
Oh, yeah, that old game.
They wanted BLT to translate its species creation math.
From binary to Python.
Right. The possibilities seem endless.
They do.
But what about the downsides? Like, what about compressed data and needing ridiculously long context lengths?
Yeah, those are legitimate concerns.
Someone on Reddit, DQU3QLS, brought up a good point about how BLT might struggle with compressed data.
Yeah, because the compression algorithm.
It could hide the information density.
Exactly.
And even with uncompressed data, processing multimedia files could need massive context lengths.
Far beyond what we can handle now.
So we're not going to be feeding BLT whole movies anytime soon.
Not yet, at least. But even with those limitations, the potential of BLT is undeniably exciting.
It is.
I think it's important to acknowledge the skepticism around BLT too.
Yeah, for sure.
It's good to have those critical voices.
Right. Keeps us honest.
Especially in a field like AI. Things are moving so fast.
Yeah, definitely. I've seen quite a few skeptical comments, actually.
Well, yeah.
Especially on Reddit. Like, there's this one user, 1313S,
right.
saying that BLT won't just magically solve all the LLM problems.
Yeah, I mean, that's fair.
Like, they were saying transformers still struggle with counting no matter what.
And there's a lot of research backing that up.
Yeah, they were putting into some research about that, too.
Like that tweet from, at Goodside?
Yeah, that one. And a paper on the challenges of character-level counting.
It was a good point. Like, maybe the BLT researchers hit those same issues, but didn't include them in the paper.
It's a good reminder that BLT is a tool, like any other.
Exactly.
It's not a magic bullet.
Definitely not.
So, no.
It has its limitations.
And we can't forget about those potential downsides.
Oh, yeah, for sure.
Like the computational demands could be a big problem.
Especially for those of us who like to run things locally.
Yeah. There was this comment on Reddit from CUDA Challenged, I think.
Oh, yeah, I saw that one.
Something like, if BLT takes off, most of us local LLM folks are out of the game.
Right, until the hardware catches up.
Ouch.
Bit dramatic, maybe, but...
The point stands.
The point stands, yeah. Running BLT at scale, it'll probably need some serious hardware upgrades.
It's going to be a challenge. And even with the best hardware,
yeah,
there are still fundamental issues with how LLMs work, right?
Oh, absolutely.
I remember this Hacker News comment. It really got me thinking.
What was it about?
It was about Microsoft Copilot.
Okay.
And how it couldn't sort U.S. states by water area.
Oh, yeah, I remember that one.
Like, it claimed it was super confident.
Very high probability of success or something like that.
Right, but then it just messed it up completely.
A simple sorting task.
It shows you, like, they don't really understand their own limits.
That lack of self-awareness.
It's kind of worrying, actually.
It's a bit concerning, yeah.
So it brings us back to that big question. Is BLT just doing the same old stuff, but faster?
Right.
Or could it lead to something more profound? Like a truly universal AI?
That's the $1 million question, isn't it?
It is. Some people think.
Yeah.
Because BLT works at a lower level.
With bytes, not tokens.
Right. It could be the key to a more general AI.
Maybe even emergent AI.
Emergent AI, what's that?
It's a bit speculative, but Imagine a model that develops abilities beyond what we programmed it to do.
Wow. So, like, it just figures things out on its own.
It's a possibility. Like, by removing those token limitations and giving it all this raw data, maybe it could uncover patterns, relationships that we haven't even thought of.
That's both exciting and a little scary, honestly.
It is a bit of both, isn't it?
Like, what about control?
Right.
Safety. If these models start doing things we don't understand.
Yeah, that's a huge question. We need to figure that out.
As we develop these powerful AIs.
Responsible development. That's key.
Absolutely. So we've talked about BLT conceptually, but how does it actually work?
Yeah, the paper's pretty dense.
It is.
But we can break it down. So let's go back to that encoder structure.
Right.
It's the core of BLT's learnable tokenization.
Yeah, the encoder analyzes the bytes and segments them into those patches.
Exactly. But instead of fixed tokens, the encoder creates the patches dynamically.
Based on the information density.
Right. It's like, think of a composer.
Okay.
Arranging notes into measures. Each measure has a balanced amount of information.
I see. And what about the decoder?
The decoder's like the orchestra, bringing it all together.
It reconstructs the original message.
From those patches, yeah.
Okay, so how does the encoder decide where to divide the bytes?
Right. Good question. It uses byte-level entropy.
Right. But how does that work in practice?
It predicts the uncertainty of each byte. So if it sees a predictable sequence, like a common word, it groups them into a bigger patch.
Without losing information.
Right. But for unpredictable sequences, like a rare term, it makes smaller patches to capture that concentrated information.
So it's always adapting.
Yeah, shrinking and expanding the patches, like breathing.
Taking in the predictable and then
Exhaling when it hits something new.
Wow, that's a great analogy.
It is, and that's how BLT gets its efficiency.
By focusing the resources where they're needed.
Exactly. No wasted time on predictable stuff.
It's really different from the old way of tokenizing.
It is a major departure.
I'm curious about the code. Did you see any of that?
Not the full source, no.
Right.
But there's a breakdown of the directory structure on GitHub.
Oh, yeah, I saw that.
That Byte Transformer.txt file.
Yeah.
It shows how the code base is organized.
Like the folders for data handling, the model definition.
Tokenizers, pre-processing, even some example applications.
Looks like a standard Python project.
Yeah, at first glance. But there's some serious engineering under the hood.
Oh, for sure. All that entropy calculation, patch creation, training.
It's a complex system.
Very complex. I saw some file names like linguatrain.py and vol.py.
Probably scripts for training and evaluation. Pretty standard stuff.
Right. And then there were terms like FSDP grouping plan and T-parallelize. That's for distributed training, right?
Absolutely. You need that for these massive models.
To handle billions of parameters.
Yeah, imagine training that on a single GPU.
It'd be impossible.
Pretty much.
It's mind-boggling.
It is.
So even though we haven't seen the actual code, it's clear BLT is a big architectural step forward.
It is. And I think its implications go beyond just performance.
Oh, how so?
It's changing how we think about AI processing information. This move from fixed tokens to a dynamic byte-level approach, it could lead to a more general, adaptable kind of AI.
This idea of a universal AI processing all kinds of data.
In their rawest form.
It's really compelling.
It's a future worth exploring. BLT might be the key to it.
By going back to the byte level.
Yeah. It's an exciting time.
This deep dive has been amazing. Thanks for joining us.
My pleasure.
And to our listeners, keep learning. Keep questioning.
Keep pushing those boundaries.
The future of AI is unfolding, one byte at a time.
I like that.
And that concludes our deep dive into BLT. Until next time, keep exploring.